Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your day to join us for this month's installment of Thirsty Thursday. Before I begin, I do want to call attention to a couple of upcoming events. The next Thirsty Thursday will take place on December 10th at 1 p.m. Eastern Time. Acoustic benefits achieved through glazing will be presented by Julie Schimmelpenny of Eastman Chemical Company. This will be a 45-minute presentation and available as this presentation has been through glassbuild.com as part of GlassBuild Connect. Speaking of GlassBuild Connect, it is still open through the end of the year, providing registered attendees on-demand access to more than 70 educational presentations and products and services from 300 plus exhibiting companies at glassbuild.com. We are also excited for our best of version of the traditional winter NGA Glass Conference that we'll be offering online on February 9th. Registration is open, and we sincerely hope you'll go ahead and put a placeholder on your calendar today for this. We will address questions at the end of the presentation. In your Zoom toolbar, you'll see the Q&A button. Please enter your questions there at any time throughout the program. I'm now pleased to introduce our speakers. During his 35 years at WJE, Mark Schmidt has focused on the assessment, preservation, remedial design, and implementation of restoration programs for a variety of building envelopes. He has led hundreds of investigations addressing operational concerns, such as water infiltration and corrosion, safety and structural concerns, such as glass breakage, anchorage, and component failure, and aesthetic concerns, such as finish or surface degradation. He has specific expertise related to the assessment of architectural and glass components. Dr. Stephen Morse is an assistant professor at Michigan Tech University in the Department of Civil and Environmental Engineering. He has extensive experience in model scale and full scale testing, numerical modeling, and software development related to window glass strength. For the past 12 years, Dr. Morse has served as a technical advisor on the ASTM subcommittee responsible for maintaining and updating the National Window Glass Standard ASTM E1300. He contributed and authored key provisions to the E1300 standard, including the addition of a generalized analytical procedure, expanded NFL charts, and updated examples. Dr. Morse also serves as the convener of Workgroup 1 of ISO Technical Committee 160, Subcommittee 2, Strength of Glass in Buildings, and is a member of the U.S. Technical Advisory Group. Mark and Stephen, welcome.
Thank you.
Thank you.
That was a mouthful, Sarah. Thank you very much for that nice introduction. Stephen and I are excited today to be talking to you about what appears to be a timely topic. We hear from Irmela that one of the most requested documents, at least downloaded documents from NGA, is the document concerning glass cleaning, a joint document by the NGA, IWCA. And as you will see during the course of this presentation, cleaning operations do account for a considerable number of the glass surface blemishes, at least the ones that we've investigated. We're going to dive into not only how to evaluate the blemishes themselves, but also how to restore them and to evaluate them structurally. We've got the term damage in quotes there at the bottom of the screen because damage is really a legal term that's spelled out in many construction contracts. Blemishes are what's referred to in the applicable ASTM standards. So we'll leave the damage assessment to the lawyers, but we'll talk about the blemishes specifically unless we slip up and use that damage term occasionally. Here are the learning slipped ahead there. Here are the learning objectives, and we're not going to read those in detail, but suffice it to say that we'll go through the types of blemishes and polishing methods and ways to evaluate whether they're still structurally adequate. Now, our WJE marketing department wasn't too fond of me coining the term glassets with fear that I might mispronounce some of the embedded words there. But the point is that I hope will be a catchy phrase for you, is that there's all of us have glass assets. And we'll get into it in a little bit as to why they're so significant on new and existing building projects. Then we'll take a look at various causes of glass damage with the ever popular Believe It or Not. I'm sure you'll be on the edge of your seat wondering what that's consists of. Then we'll look at assessing the quote damage, or determining what types of blemishes are acceptable or not acceptable. And then we'll dive into the remedial options. Stephen will then bring us to the point of analyzing how we can tell if the glass is still structurally adequate after polishing, and give some brief examples by way of a case history. So with that, let's take a look at why glassets are so significant. I cribbed this image of a building off the internet. It's a building in Hong Kong, but it will serve to demonstrate my purposes here, and that is, for many buildings, the envelope costs represent about 15% to up to 25% and greater of the overall building costs. So you can see it can be very significant depending on the ornamentation and what we call jewelry on the outside of the building. A significant impact to that overall envelope cost is the glass. In recent years, for a variety of reasons, glass has gotten more complex. There's more ornamentation, there's more custom fritting patterns, there's a more variety of fritting patterns on a given building, which drive up the costs. Then there's also different types of laminates and glass filling and blast resistance requirements. And what we're finding out is that on most projects, except for maybe a few recently that I've seen sourced from China, there's limited or no attic stock provided at the end of the project that you could utilize to replace any glass that might be blemished or damaged. The glass itself, because the reasons noted, becomes harder to match, longer lead times, especially when sourced internationally. And then the ubiquitous use of unitized systems with structural silicone glazing and maybe some nearby high-end finishes on the inside can make it very costly to replace any glass. So glass not only becomes an asset, but it also can become a liability. Let's take a look at the reasons we're often seeing for glass blemishes. Some occur during construction. This particular example here, you can see some small burn marks, pit marks in the glass surface. This will be an example that Stephen uses at the end of this presentation. But you can see that that's occurring on glass that has a fritted pattern. The particular building had a variety of fritted patterns, which made it very difficult to get replacement glass for the project. So what caused those pits? Well, apparently the workers didn't think it was a wise thing to point the chop saw against the drywall and potentially damage that, so they oriented the chop saw and cut at a variety of metal studs and the like, broadcasting small bits of burning metal against the glass, which of course we know that doesn't play nicely together. Construction cleaning, you would gather, should improve the overall appearance of the project before handing it over to the owner or developer. But we're finding that construction cleaning accounts for most of the construction blemish projects that we get pulled into. Some of these seem pretty benign. We're zoomed in pretty far. The scratches are pretty faint in these 3 photographs. There's some debris that's hit the glass on the left-hand photograph during construction. But it can become very extensive. As you can see in the right-hand photo, under sort of nondescript, cloudy day conditions, the glass scratches are very prominent. In the case on the left, we almost left the project without identifying any egregious surface blemishes until fortuitously the sun came down on the horizon and illuminated these, what we would term angel hair scratches on the glass, and they were widespread and over the majority of the glass surface. So you can see that lighting conditions have a significant role in the identification of scratches and blemishes as well. Then there's blemishes that occur from what we would term normal operations. In this case, there's unprotected cementitious materials, precast concrete, that's in the same plane as the glass. And what occurs is rainwater runs over the surface of the concrete, leaches alkalis out of the concrete, and deposits them on the glass surface. So they end up looking like water spots, which you think might be pretty easy to remove just by normal window cleaning operations, but they can't. In fact, when we've looked at some of these projects in the laboratory under the microscope, we can see that the alkalis have in fact etched themselves into the glass, creating a small pocket in the glass surface. Then, in an effort to try to remove such water spots from the glass, this is a project where an owner-developer hired a cleaning contractor to remove those water spots. What they ended up using was a proprietary glass cleaning material that contains silica, which we all know is a component of glass, has the same hardness of glass. They use that material on the end of a handheld polisher, and you can see the overall pattern that they used as they were going across the surface of the glass. Believe it or not, this was a mid-rise building, and this condition was not noticed until pretty much the whole project was completely cleaned and had these type of fine scratches. They ended up being very shallow in this case, only about microns of an inch deep. So other types of blemishes can occur from natural disasters like hurricanes, like tornadoes, microbursts, even derechos, a term that probably few of us used before this last tornado season in the Midwest, where there was several derechos that we've investigated. The kind of debris or conditions that you might see from natural disasters could look like this. This happens to be a prominent hotel in Atlanta during some rash of tornadoes that came through there some years ago. And the kind of blemishes that you see are pretty widespread because of the airborne debris that typically is associated with tornadoes. What Stephen and I have found is that, we've highlighted the blemishes there on the right-hand photo in some on marker, using marker. But depending on who the occupant is of that particular space, if it's an office worker, a tenant, somebody who's not just kicking up their feet and looking out of the window, that type of damage could go largely unnoticed. Whereas if it's a multi-million-dollar condo owner, those blemishes become very significant in their eyes. So here's another condition where there was a building in the way of a relatively wimpy hurricane, Wilma, that came through Miami several years back. And while that might look like different colored glass on the side of the building, it's actually boarded up windows because of extensive glass damage that occurred there. It was a brand new building under construction. The problem was there was another hotel upstream from this building that lost a lot of glass and those projectiles were hurled against the side of this building, causing not only glass breakage, but glass surface blemishes, such as this rub shown in the upper right-hand slide. Rubs are typically shallow abrasions that are generally wider than scratches, but perhaps not as deep as scratches. And also associated with these kind of storms that have a lot of windborne debris are what we would call crushes. They're a form of point blemish. They're a result of small impacts of debris, in this case glass, from the upstream hotel that hit the side of the building. Then we've seen a lot of blemishes resulting from facade restoration projects, because on those particular projects, you are also using repair materials that can be cementitious or just paints or coatings or a variety of things that can get on the surface of the glass. And these two devices or implements, the safety blade there on the left and the 6-inch wide scraper on the right, can be used by construction cleaning contractors to remove tenacious debris or perhaps cementitious debris from the glass. They're part of what NGA would term non-routine cleaning. But then there's pieces of equipment or tools that you wouldn't expect. Some 3-in-1 tool there, a pry bar, and my favorite is the rusty tile scraper. And yes, that tile scraper is only really intended for use on floor tile, but it was used on a particular project, as we can see here. The rusty tile scraper was still in the gang box of the contractor that cleaned the glass. And we still had some of the material that had been used as part of the facade restoration project. So we broadcast that against the glass and used the same device, same piece of equipment to remove it. And lo and behold, we were able to replicate those scratches that looked very similar to the rest of the documented scratches on that particular project. And then lastly, under the believe it or not category, there was a NFL football team out west who was not really accustomed to winning many games, but they managed to pull one out, and an overly exuberant fan detonated some fireworks in close proximity to some buildings, including the subject building that we worked on, which was a mid-rise building. And as a result, you had these almost firework looking little bits of metallic embedment in the glass as a result of those fireworks. And that was extended all the way up to and above the 15th floor of the building. So now that we've taken a look at how we can develop some of these blemishes, how do we determine whether they're acceptable or not? Well, there's only one standard currently available. That's ASTM C1036. It's currently under revision. Those standards are required to be revised every 5 years. And there has been some discussion in the committees that I've participated in to the eventual development of a standard that might be more suitable for use on in situ buildings. But nevertheless, the standard itself says it's applicable to field use, and it's the only one we have at this point in time. So most of you are probably familiar with it, but it generally involves an unbiased observer that stands at specified viewing distances from the glass and tries to identify any blemishes on the surface. We typically have a recorder that stands at the glass so that the observer is not biased, and circles all the blemishes that the observer calls out. The next step would be to measure those blemishes. In the upper right-hand corner, you can see we're measuring the diameter of a point blemish. And then we also measure the distance between the point blemishes, because that is part of the criteria of the standard. For our own purposes, We also try to measure the depth of the blemish, because that will give us some idea as to how much glass polishing might be required to remove the blemish from the glass surface. And we have some experience on past projects, and it would tell us whether or not we believe it will be a promising exercise to try to polish that scratch out. Then we go into the standard itself. This is the table for point blemishes. Just about all the glass used on buildings is Q3 quality glass, architectural glass. And you can see that for point blemishes of a certain size in the orange highlighted area, they're just allowed in any number. But then further down in the criteria, you can see that some larger size blemishes are only allowed with a given spacing between them. And then if the blemishes get too large, they're just not allowed at all per the standard. Something to point out is this particular table was developed for 6 millimeter thick glass, nominally 1/4 inch thick glass. For any glass that's thicker, they're allowed to contain proportionally larger blemishes, and there's an example given in this footnote of the table. Then for linear blemishes or scratches, rubs, and the like, there's a similar table. And again, there's separate viewing distances for these type of blemishes, several different distances. If you can only see the blemish from a very close distance, they may be allowed in any quantity at all. But from further viewing distances, if you can only identify them at that location, they need to be separated by 24 inches. If they're identifiable from the furthest viewing distance, they're not allowed at all in some cases. So we've identified how we can get the blemishes, and then we've also taken a look at how to identify which are objectionable or not allowed blemishes. What do we do about that? Well, the no-brainer solution would be to replace the glass, but as we've discussed earlier, that can be a very costly proposition given the types of glass, the types of glazing, the access, etc. Secondly, as we've seen in one example so far, proprietary cleaning compounds have caused more damage than good in most cases that we've seen, particularly cleaning compounds that have silica or hydrofluoric acid in them. So that leaves polishing procedure where the final process involves a cerium oxide type of finish. So let's take a look and see how that process works. You can see the operator in this case using a handheld polisher with some sanding discs on the end that have a variety of grit to them. Starting out with very coarse grit and moving to fine grit, the operator first of all gets to the bottom of the scratch and then feathers that area out to the adjacent unpolished areas. We also, as a precaution, take the surface temperature of the glass during these operations. Rare instances does it get up to 300 degrees, which is much lower than, say, even heat soaking glass. So there's no real danger of real stress relaxation of heat treated glass products. And now I would like to show a video of this in operation. Okay, here we go. Sorry about the mix up there, but you can see the operator here is starting out with a rough sanding disc, and he's roughening up the area and will proceed with feathering out to the adjacent areas. What Stephen and I have recently witnessed on a project out west that we're just finishing up is that this process is very workmanship critical. It looks like this operator could do this in his sleep, but if that polisher is not held flat against the glass surface, you can develop some ridges and areas of distortion that will be nearly impossible to get out. So here he is in the final process using a cerium oxide solution on a felt pad on the end of a polisher to restore the glass to optical clarity. And he's making it look pretty easy, but as we've noted, it's not as easy as it looks. As part of the final process, he's going to use a mop head and a squeegee just to make sure it all looks good. And lo and behold, he found an area that he's not pleased with. So he diligently goes back after it. So there's no indication of the glass blemish after he's done. That process with the cerium oxide paste can be somewhat messy depending on the operator and whether you're doing that on the inside or outside of the building. So here's another method that we have used. It's an automated polishing procedure where there's a shrouded area that you can see of the device. Underneath the shroud is a spinning felt pad, and cerium oxide slurry is being recirculated under the shroud, under the pad, and back to a bucket. So this process we found is less workmanship critical. However, the equipment is much more finicky. So the equipment was developed for use on car windshields, and if precautions are not taken, you'll burn it out. It's not really meant for use for 6 to 8 hours a day on the side of a building. So that has to be accommodated. But it's a much cleaner process when they're done. The device is pulled off the glass. There's a very small drip of cerium oxide slurry that's easily wiped up. And this is a project I showed earlier where the damage was done using a proprietary cleaning compound. And we used that automated procedure in these boxed in areas. Now, this is not the final product, but you can see that there's a huge improvement in the overall aesthetics and optical clarity. That was as a result of a vertical and horizontal pass using that equipment. It was found that another horizontal and vertical pass were required for all parties to accept the final results. With that, I will now turn it over to Stephen, who will cover the structural implications of the glass polishing. Now that we're completed, have we left the building and the glass in a condition where it's structurally adequate? Stephen?
Thank you, Mark. So I want to kind of walk through, so now that we've polished it and we've shown that we can actually repair the glass or remediate that blemish, we want to make sure that, we were actually removing glass material. We want to make sure that the glass can still withstand the design loads that's required, when it was installed. And so in the US, we've been using ASTM E1300 to specify glass thickness for windows in buildings. And recently, we've added a new analytical procedure to the standard that's going to allow us to actually assess some of these changes that we're doing to the glass, and namely that we're reducing the thickness in localized areas, and correspondingly, we're likely reducing the heat treatment layer that is at the surface of the glass as well. And so we want to make sure that we can we can calculate and show that the glass is still has the appropriate capacity to stay on the building. So I want to just kind of orient us to kind of some common language. I'm sure many of you already know some of these terms, but just in case we don't, I want to go through it. So glass that's used on buildings, at least for infill panels of windows, typically always starts in some fashion as annealed float glass. And depending on its usage, it may require it to be heat treated. There's various reasons why we would use heat treated glass on building, either for design load resistance or for safety considerations, especially for floor to ceiling interior units. And so when we heat treat glass, what we're doing is we're heating it up to a near melting point or almost softening point, and then we're going to cool it down very quickly. And depending on the rate or the intensity of that cooling, or quenching, it imparts a RCSS, a residual compressive surface stress, into the glass, and the magnitude of that has to do with that cooling process. And so one of the things we need to know to do a before and after with our polished glass is we need to know what the actual RCSS is on our piece of glass. Okay, so this is measurable. There are several devices out on the market that allow us to measure this. And in the United States, we specified two different types of heat treated glass. You have heat strengthened and we have fully tempered. And those are distinguished in C 1048 based on the magnitude of the RCSS. Now, in other standards across the world, heat-treated glass is specified in a different way. But for our purposes, we're interested in what is that measured RCSS value. So I have over here on the right is a chart that goes to the depth of the glass. So at the top, we're saying that's the top surface where the device is touching, and then it can actually kind of measure through the surface of the glass to come up with both the magnitude of the compression and the tension layer within the glass. Okay, so we're going to come back to this one, but just know that we can measure that, and that we would like to know what it is actually for the piece of glass that we actually have on the building. So when we use the analytical procedure of ASTM E1300, and I don't want to dig too deeply into these long equations, but what it allows us to do is to account for the geometry, that's including the long and short dimensions. We can actually incorporate different edge conditions or edge support conditions, and also account for the duration of the load. That's what this TD is there for. And we can also include the RCSS. Now, when we use this method for design purposes, the standard requires us to use the minimum RCSS values that are specified in C 1048. So that'd be 3,500 PSI for heat strengthened glass, and that'd be 10,000 PSI for fully tempered glass. But in our experience, we found that often glass is not at the minimums. There's something above that. But we do know that, for design purposes, you never know what you're going to get on the job site. So it's best to design with the minimums. But for our purposes, when we're going through and checking, do we still have capacity? We want to show that the glass that's actually there has capacity. And so we have the ability to just use the actual RCSS that we measure on the glass, both before and after. Just a few more details. The way this is used is we would use a finite element package or some other numerical stress analysis package to calculate the stresses across the surface of the unit for various loads or the design loads. And we also get the respective areas. Okay, so the key thing with this method is that we don't go and find what is the maximum stress across the entire unit and say, that's what I'm going to design to. We're going to actually take a probabilistic approach and incorporate all the stresses at all locations on the glass, and then we're going to bring those together in a stochastic analysis, and that's basically what this embodies here. And if you want more information on that, I'm happy to discuss those with anybody later on. So again, RCSS is here. So as we move forward, the way we would actually, if you want to do kind of an example of how this would work is that I'm going to start with some piece of glass. So I'd go and find the rectangular dimensions and the thickness of the glass. I would know the design load, and I would perform some numerical stress analysis. And so we get our nice rainbow pictures out of these, and I'm sure many of us have seen before. And then we can take the data from that analysis, and then we can plug it into our glass failure prediction model, that equation that I showed previously, which, for as nasty as it looks, you can actually type all those equations into Excel and actually do the calculations there. So we don't have to have fancy software to perform that calculation, other than the fancy software that requires us to do the stress analysis to begin with. And then what we're looking for is either we're greater than or less than 8 in 1,000. So E1300 specifies this kind of cutoff point that is said if our probability of breakage that we calculated is less than 8 in 1,000, then our design works. If it's greater than 8 in 1,000, then we have a problem. So this is going to be our check that we need to show that post-polishing, we still have a probability of breakage that exceeds 8 in 1,000. And I'm happy to discuss any of this process later on in more detail, but we're going to leave it there for today. So moving forward, when we polish glass, so we have this blemish, when we polish heat treated glass, what's going to happen to the glass physically? So we need to understand that. So one thing is that we immediately recognize that we're removing glass materials. So the thickness of the glass has changed in the area that we polished. Now, in many of the projects that Mark and I have worked on, typically the places in the glass that need to be polished is not the entire surface. Mark showed one of his examples where it was effectively the entire surface, but usually it's in some smaller location at a particular point on the glass. Now, with addition to removing the glass material, the glass itself, correspondingly, we're going to locally reduce that RCSS as well, because we know that that was a function of the its depth through the glass. And there's a few issues that come into mind when we think about this. It's like, well, that stress had to go somewhere to balance our internal stresses. So we need to be careful on what we assume. Is that going to be that change? Okay, so one, we need just to know how much was it, the thickness, and it'd be nice to know how much RCSS through direct measurement was reduced. So Mark mentioned we wanted to kind of walk through a case study to kind of illustrate this. So we have been measuring the thickness and the glass, the RCSS, the residual compressive surface stress, using a optical device. In this case, it's a scalp, and the scalp plugs in through USB to a computer, and then it's able to perform the measurement, and we get a nice fancy drawing here of that stress profile through the thickness of the glass. Okay, so that's where our picture came from previously, was from this device. And with that information, we were kind of brainstorming kind of from before we polished, what could the RCSS end up being? Okay, so before I get into that, I want to just orient you to my columns here or my axis, excuse me. On the x-axis, I'm showing a ratio of my thickness being reduced. So think of it as like this was our original thickness, and as we continue to reduce the thickness through polishing, we're moving this direction. So this is the most that we remove. Now remember, this is a ratio, so these aren't actual dimensions. On the y-axis is where we started with what is the original RCSS, and as we do polishing, then it would reduce going down, okay? So for this first one, this gray one that we talked about is where we kind of anticipated, well, if we just use the graph that we had measured, then we could kind of estimate or extrapolate where we think the RCSS would go with that. And what we found there is that, well, as we anticipated, that does not in any way address the rebalancing of the stresses locally through that thickness, because if we still have the full RCSS on one side, it's got to rebalance. So we attempted to do a little bit of algebraic magic and see if we could come up with another model that tried to address that. And that's this orange line. And so we said, well, we want to see how does this compare? And so when we actually measured it, we found that our original, when we just barely took anything off, we were like, well, that's reasonably close. But we found very quickly as we continue to move more glass material, that RCSS drops significantly faster than even our algebraic attempts of coming in. So we know that there's more going on here than we can just predict right now with kind of our rudimentary attempts at the model. And a few notes here is that this kind of indicated to us that we really need to measure these things on a case-by-case basis, because we don't know. Oftentimes, we found that the client or the drawings or otherwise don't always identify correctly what glass is actually on the building. And two, we have no way of knowing what the RCSS is when it's heat treated until we actually go and measure it, because all the manufacturer has to do is make sure they exceed the minimum. And so we've kind of come to the conclusion that we really have to just go out there and measure these things on a case-by-case basis until we get, maybe sometime in the future we'll get a sophisticated enough model to where we can identify these things, but we're still likely going to have to figure out what the RCSS is initially, even if we do have a more sophisticated model. It's also worth noting that down here for this particular project, we had removed almost 1/100 of an inch of glass. Again, this is a ratio. This isn't the actual value. And so we know that we can go that far and still not have excessive distortion on that, and we can still have reasonable strength. And this was 1/4 inch glass. So if we actually go thicker, then one could probably actually go even deeper than that, as long as we could maintain that, limit that distortion, because we don't want to just grind a lens into our window, because people are going to notice that when they go by. All right, so now that we know what the change in the thickness was and what the change in the RCSS is, now we want to go and reapply our glass failure prediction model. Okay, so in this case, we said our max reduction was, in this case, it was 0.008, so that's close to that 1/100 of an, or 1/100 of an inch that I was talking about. And we had a corresponding reduction of 28% in our RCSS. So that's a pretty big difference. So certainly if we were at the minimum of 10,000 and we reduced it 28%, we're clearly not in our minimum 10,000 range. Now, it's also worth noting that when we polish glass, as I mentioned, we're typically not doing the entire unit. We're using some localized area that we're trying to get rid of these blemishes. So it depends, again, going back to that case-by-case basis on what's going to be reasonable or not reasonable as far as this goes. For our analysis purposes, what we decided to do was, it gets kind of iffy to try to do plate analysis with a varying thickness in the middle of it. And we felt like, that's probably just unnecessarily complicated. Why don't we just assume the entire plate now is the reduced thickness and has that reduced RCSS. And we'll do our analysis based on that information. And this way we know that whatever number we're getting is likely way lower than it actually is, since often we're just doing a small area. But, and it's likely going to cover any other secondary effects that maybe our, if you will, relatively simplistic approach so far addresses. We feel like we're in pretty good shape by making this assumption. So with that, let's put some numbers to it. In this case study, this actually goes back to that chop saw blasting hot metal into the interior fully tempered piece of glass. And so what we're going to be focused on here is this 1/4 inch fully tempered interior piece of glass. And what we were trying to get rid of was that something not unlike weld splatter that was coming off of that chop saw. And we have various different light sizes as we would anticipate on a new structure these days. So because of the age of this building and when the actual initial designs were, it was likely that the glass was designed in accordance to the basic, what is now called the basic method of E1300 in 2016. And this is corresponds to the previous editions. This was kind of the standard where we go into those crazy squiggly charts and we get a non-factored load, and then we multiply it by a glass type factor, and then we do our load sharing for insulating glass units. So for these particular units, we went ahead and just did that just to double check, were these things actually originally adequate to begin with? And we had access to the wind loads based on the original construction drawings. And we found that indeed they were, but we did find, especially with this first one, that they were quite close. There wasn't a whole lot of residual capacity according to the basic method. And so certainly that would cause some concern, is like, well, if we're reducing heat treatment or if we're reducing the thickness, so on and so forth, is that still going to check? And so it would have been nice to just continue to reuse the basic method to calculate this. But the basic method doesn't allow that because we have all these pre-calculated charts in there. It's also worth mentioning that those pre-calculated charts are based on the C1036 minimum thickness standard for float glass, which in practice we find that most glass is often a few thousandths of an inch thicker than the minimum. And so right there, we know that we already have some extra residual capacity. But again, that's one of these things that we can't assume. As our production lines get more efficient, I anticipate that extra residual above the minimum is probably going to reduce to much closer to the minimum than it already is. But that's just my opinion. Somebody else probably could speak to more on that. So we can't do anything here. So the question is, can we go ahead and use that analytical procedure? So indeed we did that. And this is what we came up with that original design capacity. So what we did here was use the measured RCSS values and the actual measured thickness that we had and ran through the analytical procedure. And we came up with these values. So we have a significant increase in the actual design capacity for these units. And this is a known artifact of the analytical procedure. And it speaks to that the glass type factors that have been used in the past were really conservative. And some of our colleagues will indicate that that was fine because we're going to run into deflection issues eventually anyway. But remember, in our case, we're just looking for what is the capacity. We're not looking at, in this case, serviceability issues right now. And so what we did is we went ahead and applied the post measurement data. And we see that, in fact, those did reduce, but they did not reduce much. In fact, it was about a 3% reduction in that capacity. And those are still well beyond, almost double in each case, the original design load. So we resolved in this case that there was plenty of capacity post polishing for this test case. So that's great. So what were our project outcomes? How did this end up for us? Well, we were able to go through and take what were blemishes that were well beyond the allowable limits of C1036. We were able to mitigate those, or I guess remediate those is the word I should use, and return them to optical clarity as we've discussed and shown. These happen to be highly customized units. There was over 50 patterns on this project. You saw that there was at least 4 different sizes of units that we were addressing, and there was a bunch of them. They had damaged over 450 of these units before they got a hold of that chop saw guy and stopped him. And so again, we actually, in this case, had a out-of-town contractor that's willing to travel to locations to do this restoration. So that's cool. Project cost savings. Well, as Mark indicated before, these really nice facades can be a liability, and they are quite expensive, especially if we start shutting down roads or getting cranes involved and trying to replace this. Certainly a significant cost at the order of 450 units. I mean, that could be the entire building or at least half of it. So in this case, we reduced the cost down to about $1,500, or without per diem, $1,100 per unit. So that's still a big number, but that's a whole lot less than replacing the entire facade. And so in this case, it was a 5 to 10 times a reduction in savings. Okay, so that's a huge difference on that one. So what are our takeaways from this? We're going to sum up with our Glassets. Number one, we've indicated that these glass facades, while beautiful and really striking, make our buildings stand out, they are expensive and they are very costly to replace, sometimes more costly to replace than they were initially to install, and because of site conditions and so on and so forth. The polishing can be a cost-effective method, and it can be also still structurally adequate. So we don't have to go in and replace all this. we can do this. Now, again, we say this is a case-by-case thing, and so we recommend that you perform a mock-up and test measurement, figure out what kind of glass you have on there, and make sure that when we're done, that you're going to have the look that you desire. And one other thing that I just want to kind of remind everybody that Mark mentioned earlier was that this is highly workmanship sensitive. You have to have the right professionals on the site to do this, to come out with a good product, because if you just get somebody that hasn't really done this, they can grind a lens into your window, and then you really do have to replace it, because that's almost not fixable. So with that, I think we're going to hopefully take some questions, and we appreciate your attendance. It looked like there's over 64 of you on with us, so that's awesome. So thank you for being here.
Yes, agreed. Thank you, Mark and Stephen. Let's dive into some of the questions we've received. First one, have you ever implemented an epoxy filler, such as that used in windshield crack or chip repairs?
Mark, you want to take that one, or you want me to?
I can take that one.
Okay.
Most of these are scratches, longer scratches, more egregious scratches. It's not the typical just one piece of debris that hits your windshield that we're trying to repair. And furthermore, the polishing process is more of an accepted restoration technique by glass producers and fabricators of architectural glass, rather than the epoxy filling is more of an automotive repair technique.
Okay, thank you. Another question, can you and how do you determine if a blemish is pre-installed or post-installed origin?
I can take that one too, Stephen.
Yep.
It's mostly anecdotal. If we can try to replicate the scratches on site using the equipment we know that was used or available at the time. And if it's not possible to do the replication on site, we'll bring the glass sample into our laboratory. Right now we have about a 5-foot by 12-foot IGU that we've been experimenting with in the lab, and then we'll bring it outside on an A-frame and take a look at it under ambient lighting conditions, which have really, in this particular project, have revealed a lot about how the scratches probably developed. So it's more anecdotally and putting it together forensically rather than being able to identify something materially and try to date it that way.
Okay. Next question. Do you think some of the variation in empirical RCSS data could be due to natural instrument or user variance? From what I remember from the question submitter, what they remember in using Scalp, there was some variation in readings taken on the same light at different times, or multiple readings taken at each thickness ratio.
Okay, I'll take that one. It's a great question. You are exactly correct that the Scalp does kind of give slightly different readings, sometimes more so than we prefer. And so it's important to note that these optical devices do have limitations. And so one of the things that we do there is try to be careful of the level of precision that we attempt to tie to this. One hedge against that. So first, the short answer is yes, multiple readings are taken. You can set the device to cycle through a series of kind of rapid readings, and as long as those are fairly consistent, then we feel like we have a good reading. And then when we go back, obviously we've changed the surface, because we've polished it, so there is that issue. So we'll take the readings again, and I feel like that we get measurements that are still kind of within that precision that the device actually, I think, reasonably delivers. And there's been some cases where we go back and we measured and the value is higher. Okay, so we feel like, all right, well, that's kind of in the noise. It's usually not much higher. And but I would say in general, we do see the delta, the decrease. And so what we've done on project with multiple units being polished is that we we have the option of taking, well, whatever the max was of any of them. We can go, because usually we're just doing a small sample. We're not measuring all of them. We're just kind of doing this as a pre. But we'll take the max reduction and we'll just check everything with that max reduction, kind of with the idea that, well, if we think this is the worst case we've seen or likely to be, then everything else should be fine. So that's a good comment there. I think I addressed those.
Okay. Also in regard to the RCSS data, post-install cleaning, do you think that will drive more glass from being heat strengthened to fully tempered?
So
I don't think so. Do you,
I
Stephen?
don't think so, because we've done this with some heat strengthened glass. There is some residual capacity there. Also recognizing that with the heat strengthened glass, in my experience, isn't sitting at the bottom edge of the limit of 3,500. It's usually several thousand above that. And so, in fact, sometimes we get it above what is the top limit of heat strengthened glass. We've seen that too, even though it's marked as heat strengthened. And so that's another set of issues. But so I don't think so.
And upgrading it to tempered glass has its own
disadvantages. Yeah.
In terms of susceptibility to nickel sulfide contamination and such.
Yeah.
Okay. And how does laminated glass affect this conversation?
I don't think we've tested any laminated glass, but I'll let you speak to that, Stephen.
So I don't think that we've directly polished laminated glass. So first, we recognize that we typically don't laminate fully tempered glass, although one can. But we certainly do see heat strengthened glass. And with respect to, say, windows, I think probably somebody would correct me for a while, balustrades are often fully tempered. But and so I would say that we don't anticipate any difference, other than depending on the device we're measuring the RCSS with, we may not be able to measure that accurately. So in the example that I showed today, that was the Scout 4, and so that one shoots completely through the piece of glass and bounces off the backside, and that interlayer interface can interfere with its measurement, and often does. We also have the newer version of Scout 5 that doesn't go all the way through it, and so it can deal with laminated glass reasonably well, as long as it's 1/4 inch or thicker. But there's ways around that. It does preclude, in general, the use of the gas, because depending on what the interlayer is, the tin side of the glass is usually not on the number one surface, and so that makes it a little more difficult to measure that. The Scout does not have that limitation. Yeah, I think that addresses that one.
Okay. I think we have time for one, maybe two more questions. And if we don't get to your question, know that we will follow up with you via email. So next question, how closely has visual distortion been studied, understanding there's a minor depression that's created upon scratch removal or polishing?
Maybe we can tag team that one, Steve.
Yeah, definitely. I have some opinions.
A recent project we were on, we just used the ASTM C1036 criteria without a zebra board to try to detect distortion. In that case, we were looking through the glass in transmission out at some other buildings that did have some linear features that would allow you to identify any distortion. So That's typically what we use. We're thinking about using a zebra board on an upcoming project in the Midwest after glass polishing. However, that's the criteria that we've been sticking with is what's available in the C1036 standard.
Right, and to kind of tee off that, this goes back to Mark's comment that there's opportunity to maybe look at making another standard that's built a little more around this in situ study, because certainly if we're on a swing stage on the outside of a building, we can't get 10 feet away from it. But we can look out of it. But all of those things kind of change the nature of this, as the people on 1036 would rightly point out. And but we also, because we're naturally closer to that, you tend to notice things a lot more. And so we have to scale this methodology to address the fact that we're likely to be much closer to it. And so there's work to be done there. The core question there, from my point of view, being an academic, is has this been studied from an academic point of view, or when you say, detailed? And I would say not as much as I would like to. And certainly there's multiple techniques that we could go in, certainly in a lab setting or otherwise, to dig into all of this in a much greater detail. And so it's certainly something I'm interested in doing. And we kind of incrementally get to do little bits and pieces as some of these project comes up. But
it's pretty much market driven, right, by the product.
Right.
So,
but to sum up what Mark said, we've been kind of using what I would call the common person test. We're kind of trying to look at this and just look at the bias and look around and just see, can we actually just see a distortion? Because if we're walking by it or we're passing by it and it just doesn't jump out at us, then the next person's probably not going to jump out at them either. So is that a fair statement, Mark?
Yeah, and I think it depends on where the glass is situated, right? If it's if there's a hallway right next to the glass and you're always going to be walking at an acute angle to the glass, that's going to make it much more noticeable if there is any distortion. So it has to do with sort of proximity and the layout of the building and such as well.
Yeah.
Excellent. Well, I think we do need to wrap the Q&A time up just because we are at the top of the hour, but to our attendees, we appreciate you attending and also for your engagement as we've continued to have questions come in. So just to reiterate, we will follow up with you via email to make sure your questions or comments get addressed. We also want to point you to a couple of NGA's glass technical papers. As Mark mentioned in the beginning, was kind of it's a complementary resource to this presentation. They are the proper procedures for cleaning architectural glass, as well as construction site protection and maintenance of architectural glass. These are both free to download at NGA's store at glass.org, and you should have links to those within the chat as we speak. Mark and Stephen, thank you for sharing your time and expertise with us today.
You're welcome. Thanks for the opportunity.
Thank you.
Thank you. Have a good afternoon.
You as well.